Welcome. So the topic we'll be discussing in this lecture is searching with non-deterministic actions. So if you recall in the previous chapter, we have discussed uninformed and informed search techniques. Whatever the problems we have discussed through uninformed and informed search techniques, we assumed that those problems were fully observable and deterministic. That is, we assumed the environment in which the problem uh, was was acting, that environment we assumed it to be fully observable and deterministic. So what if the environment is not fully observable? What will happen if the environment is partially observable, and what will happen if the environment is non-deterministic? So that's what we are going to discuss in this lecture. Specifically, we are going to discuss about non-deterministic actions. We'll not be focusing much on partial observable environment. Okay, so that is the uh, essence of the this particular lecture. So in the previous chapter, in uninformed and informed search techniques, we assumed the environment to be fully observable and deterministic. So here we are trying to understand how the behavior of the problem will change when the environment becomes partially observable or when it becomes non-deterministic. So if the environment becomes partially observable, say if the environment is partially observable, then the agent cannot perceive everything about the environment. Now the agent can perceive only few things, and few things it cannot perceive. So, so the set of possible states the agent can foresee, because the set of possible states the agent can foresee will be limited, because the agent's percept is limited. So the set of possible outcomes he can think of also will be limited. But actually, in one sense, there is an advantage of this, because it is easier to achieve the goal state, because now you don't have many percepts, you have only few percepts. But that doesn't mean that really there is no percept. As I am unable to observe the environment fully, I cannot say that there is no percept. But, of course, there are some percepts which the agent is unable to perceive. But in spite of that, as per agent's understanding, there are less number of percepts or fewer percepts, or we can say that the set of possible states is narrowed down. So in one context we can say that this is easy to achieve the goal. Okay. But this is not always the case, because sometimes the environment may behave in a different way in which you have expected, right? Say the agent is able to say this is the entire environment E, this is the agent, this is the agent A, this is the entire environment E. Let us assume the agent is able to perceive only this subset of the environment, that is E1. Now, based on this observation, the agent will decides its next action or whatever it may be. So the as long as the agent's assumption about the environment or whatever the agent perceives, as long as it is correct, it is fine. But sometimes this part of the environment may also influence the environment. Then, then the agent's action may not be that much appropriate, right? So, 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 so at some cases, there are some cases at which, with partially observable environment, the agent may easily reach the goal state, right? When compared with fully observable state, provided if this partially observable state, provided if the agent is able to reach the goal state with the partially observable uh, percepts, and the other part of the environment is not influencing the agent or the percept, right? So that's it about partially observable environment. But our focus is not on partially observable environment. Our focus will be on non-deterministic environment. So what if the environment is non-deterministic? So what is meant by deterministic environment? First of all, In a deterministic environment, the agent can the next state only depends on the current state and the agent's action. In a deterministic environment, the next state depends only on the current state. What is the current state and the agent's action? Only based on these two things, the next state will be determined in a deterministic environment. But that is not the case in a non-deterministic environment. In a non-deterministic environment, the next state will be decided by the current state plus the action of the agent plus the action of other agents also, plus the action of other agents, or there may be some other factor which may influence the environment. So it is not only these two things that influences the environment. There may be a third factor. There may be a third factor which influences the environment. So you cannot always say that if this is the current state and if I do this action, this will be the next state. No, we cannot confirm. There is a third parameter that is also going to influence the next state, right? So in that case, the next state can be confirmly known only after the action, only after the only after the agent has performed the action. The next state will be known exactly, because agent cannot make any prediction about the next state, because there is another parameter which is influencing the next state, right? So in a non-deterministic environment, so there will be some percepts which of the possible outcomes of its actions has actually occurred. That is that is there are different possible outcomes in a what is the next state, we cannot say exactly. Next state can be this or this or this, like that there are multiple options, because next state is being not only controlled by the agent, I mean the action of the agent and the current state, but also it is controlled by the by some other third parameter which can be like action of other agents or some other features. So until the event happens, we cannot know what is the next state is, right? So the possible outcomes will be known only when actually the outcome has occurred. Okay. So so that is what about non-deterministic environment. So in this lecture, our focus is on like how searching will be done in a non-deterministic environment, how we will do search in a non-deterministic environment. So in both the cases, whatever we have discussed, both the cases means one is an partially observable environment, I call it as PO, and the other one is a non-deterministic environment. In both of these cases, the future percepts cannot be determined in advance. So you cannot determine the future percept in advance in both the cases. In partially observable environment also, what is the future percept? What future percept means? What future percept means? Current state is this. Okay. In the current state, the agent is, say this is the current state. If agent performs action A in the current state, then then the next state will be something this. After becoming the next state, what will be the percept? So that is called as future percept. So in both the cases, that is both in partially observable environment and in non-deterministic environment, you cannot determine the future percepts. Future percepts cannot be determined in advance. Why it cannot be determined in advance? Because in a partially observable environment, the agent itself is only partially observing the environment. It is not fully observing the environment. So, uh, so with its partial knowledge, the agent may take an action. But whatever the action the agent takes, that may become totally irrelevant if there is some other important percept, if there is some other important percept in the part of the environment which the agent is unable to observe occurs, right? And in case of non-deterministic environment, the agent is uh, in case of non-deterministic environment, the next state not only depends on the current current state and the agent's action, but also it depends on some other third parameter that can be other agents or some other factor may influence the next state. So we don't know what will be the next state itself. As we don't know what is the next state, we cannot judge the or we cannot understand what will be the future percepts. Okay. So in both the cases, future percepts cannot be determined. So the agent's future actions depends on those future percepts. So what will be the action of the in the future? What action the agent should take, that should depend on the future percepts. So in such problems, that is, so if the environment is non-deterministic or it is partially observable, then the solution for such problem will not be a sequence. Rather, it will be a contingency plan or a strategy. So this contingency plan is otherwise called a strategy. If the solution, I mean, if the environment is non-deterministic or if it is partially observable, then the solution will not be a sequence. Rather, it will be a contingency plan or a strategy. So this is the overall view of the topic which we are going to discuss. So we'll discuss with some example. So you may be asking, what is this sequence and what is this strategy? Sequence means a set sequence of steps. So which says that you follow these steps, you will reach the solution. Follow step 1, then step 2, then step 4, then step 7, and you will reach the goal state. So this is a sequence. But a strategy means strategy. So sequence is strictly like this. It is something like a linear fashion of thing. Whereas in a strategy, we cannot give any strict sequence. So you may be knowing the initial state, then probably you may say that if s1 is if s1 is greater than this, if s1 is greater than x, then do this. Okay. If s1 is less than if s1 is greater than x, then do this, else do something else, right? So like that, there may be some set of if else rules at every state. So at every state there may be set of if else rules, or there may be nested if else rules. So such an solution is called as a strategy. So there is no straight sequence. You'll have a strategy. So if if s1 is greater than x, then s2 is equal to x plus 2, else s2 is equal to x plus 5, something like that. Again, then if s2 is greater than 10, then s3 is equal to uh, x plus 20, else so on and so forth. So at every step you'll have some if else rule or nested if else rule will be given to reach the solution. That is it is not deterministic. So that we say it is not deterministic. So if else rule, what it says, so if else is also an example of non-deterministic thing. Either this can happen or this can happen. We don't know what will happen. The if part can be true or it can be the else part can be true. That depends on the type of the input. So that is how the general if else work. So here also, in a non-deterministic problem, you cannot provide the solution as a sequence. Rather, the solution will be a contingency plan or a strategy. What is a contingency plan or a strategy? A contingency plan or a strategy is represented through if else or nested if else construct, right? A contingency plan or a strategy is represented using if else or nested if else constructs. Fine. Now let us try to understand this with an example. Okay. So yeah. So already we have discussed this vacuum world problem, but this problem definition we are going to change a little bit. The overall problem is same. So these are now we are considering this as an erratic vacuum world problem with little change in the way in which it works. So this is the at the top level the problem is same. These are the possible states the vacuum world can present. So say this is both the floors are dirty, and the vacuum agent is in the left floor. Both the floors are dirty and the vacuum agent is in the right floor. Left floor alone is dirty and the vacuum agent is in the left floor, and the right floor is clean. And this is the case where the right floor is clean and the vacuum agent is in the right floor and the left floor is dirty. And this is the case where the left floor is clean and the vacuum agent is in the left floor and the right floor is dirty. And here right floor is dirty and the vacuum agent is in the right floor and the left floor is clean. And here both the floors are clean and the vacuum agent is in the left floor. Here both the floors are clean and the vacuum agent is in the right floor. So these are the possible states. So this is same as what we have discussed already. There is nothing difference here. And these are the possible goal state, the state 7 and state 8. So these are the goal states. So that is what this diagram shows. Now what change we are making to this problem to make it as a non-deterministic problem. So we want to convert this vacuum world problem as a non-deterministic problem. For that, we are making one small change in the suck action. For that, we are making one small change in the suck action. So normally, if you recall, in the suck action, if there is a dirt in the left floor and if the agent is in the left floor and if the agent sucks, then the dirt will be removed. Similarly, if the agent is in the right floor and if the dirt is in the right floor and if the agent sucks, then the dirt will be removed from the right floor. But here we are redefining the suck action with these two rules. The first rule is when applied to a dirty square, when you apply the suck rule to a dirty square, sometimes the action cleans the square and sometimes it clean up the dirt in the adjacent square too. Okay, that is always it will clean the dirt in that particular square, but sometimes it may also clean the dirt in the adjacent square also, right? Say for example, this is dirt. Say the agent is in square A. Say this is the agent. Okay, so this is the agent. The agent is in square A. Now if you apply suck action, say that's this is A, this is B. So the dirt is in B also. When they, as per the first rule, what it says, when the agent sucks the dirt in the square A, the dirt in the square A will be removed for sure. But sometimes the dirt in the square A, B also will be removed. So from here, there are two possible cases. When you apply the suck operation, there are two possible cases. One case is the dirt in the square A alone removed and agent is staying in the square A, and the dirt in the B and the dirt in the square B remains as it is. This is one case. The second case is the dirt in the square A is removed and agent is in the square A and the dirt in the square B is also removed, right? Because the rule, now we are reframing the rule for the suck action. When applied to a dirty square, this action will clean the square and sometimes it will clean up the adjacent square also. So now it becomes deterministic. It is not undeterministic. You cannot say always when I apply suck only this will happen, or you cannot say always when I apply suck only this will happen. Anything may happen. Either this may happen or this may happen, right? So this is so to convert this problem to a non-deterministic problem, we are making this updates in the suck action. So we are making two updates in the suck action. This is the first update, and the second update is when applied to a clean square, the action sometimes deposits dirt on the carpet. So what does it mean? When you apply the suck operation on a clean square, sometimes it may add dirt to that particular square. It's not always. It's not always. Sometimes it may add dirt when you apply the suck operation on a clean square. So let us take a clean square. Okay. Say this is A and this is B. Okay. Say the agent is in A and A is clean. Say there is some dirt in B. Now what the rule says, when applied the suck operation, sometimes the dirt can be deposited in that particular square or in that particular carpet. So there are now two cases. When you apply suck, in this case, the first case is there is no dirt in A. There is no dirt deposited, and the dirt in B remains as it is. And the second case is when you apply suck, it may add some dirt in A. It may add some dirt in A and the dirt in B remains as it is, right? So, so if you see both these cases, these are non-deterministic. So from this state also, you cannot say that whenever I apply suck, only this will happen or this will happen. Similarly, here also you cannot say that whenever I apply suck, only this will happen or this will happen. No, anything may happen. So this is an example for non-deterministic problem, right? Now how now we are going to discuss like how search happens in a non-deterministic problem. So the example what we have taken is an erratic vacuum world problem. So in this erratic vacuum world problem, if you apply suck action in state 1, it may lead to it may lead either to state 5 or to state 7. You don't know which state it will lead to. It may lead, but you don't know it may. So we are including both 5 and 7. So these are the possibilities. When you apply suck action on state 1, it may take you. So these are the possible outcomes we have, 5 or 7. So what is this 157? You may have doubt. This 157 or just these numbers were borrowed from this slide. So these are different states. The states were numbered as this. This state is numbered as 1, 2. This is 3, 4, 5, 6, 7, and 8. So if you apply suck operation on state 1, this is state 1. If you apply suck operation on state 1, what are the possibilities? One possibility is only the dirt in the square A will be removed, and that is what? That is this. That is this state, fifth state. Okay. And another possibility is apart from removing the dirt in square A, it may also remove the dirt in square B, and that is what? That is seventh state. Okay. But the agent will be in both the cases. The agent will stay in square A only, in the floor A only. So these are the two possibilities we have. From the state 1, if you apply suck, you may go to 5 or 7, and that is represented as 5, 7, because we don't know where it will go. So it is non-deterministic. So we are mentioning both. Okay. So so how can we write? So this is a mathematical way of representing. How can we program it? If we start in state 1, there is no single sequence of action that solves the problem. Instead, we need a contingency plan. So if your algorithm starts with state 1, there is no single sequence of action which will solve the problem. Solve the problem means which will take you to the goal state. Okay, this is a goal state. Actually, 7 is a goal state, but there is no single sequence which will take you to a goal state. Actually, the solution will be a strategy or a contingency plan. Now, how to represent the contingency plan through a program or something, or the contingency plan can be represented something like this through a program. So what it represents, suck. It says that suck. Currently, the agent is in. Initially, the agent is in state 1. So it says that from state 1 suck. So after sucking, the what will be the result? The result can be either state 5 or state 7. We don't know. If it is state 7, it is already the goal state. Okay. You need not do anything. So after sucking, you check if state is equal to 5. So the moment you suck, there will be surely change in the state, because currently you are in state 1. When you apply suck operation, the agent will go either to state 5 or to state 7. So what is the state we are checking? We are checking if state is equal to 5. If state is equal to 5, then what should we do? If state is equal to 5, then what does that mean? Then it means that agent is in the left square and it is clean, but there is dirt in the right square. So in that case, the agent should move to the right square and it should suck. So it is something like right. The two actions should be done, right and suck. So if state is equal to 5, then we are asking the agent to do these two actions, right and suck. That is move right and then suck. Else, that is, if state is not 5. If state is not 5, I mean after the first suck, if state is not 5, then the agent need not do anything, because already it has reached the solution. So there is an just an open bracket or an empty open bracket and close bracket. So this is how this can be represented uh, when a when a non-deterministic problem happens. The solution can be represented like this, instead of using a sequence, because this is not a sequence. Here it can be either directly after suck, either this may happen, or it may follow like this. After suck, you reach state 5, then move right and suck, then reach the solution. Okay, so which is going to happen? That is strategic. That is strategic. So this is how we can represent such strategic or contingency plan. So in program, how to represent this? So the solution for non-deterministic problem can be represented through nested if then else statements. Okay, they can. So basically, these nested if else statements, they represent trees rather than sequence. So this nested if else structure, they are not sequence. If you represent it as a data structure, they are like a tree. So for example, if, what you call, so first we are applying some action. After that, if state is equal to 5, if state is equal to 5, then do this. What? Move to the right and suck. So this is what if state is equal to 5. If state is equal to 5, else if state is not equal to 5, if state is not equal to 5, then already you have reached the goal state. So go to the goal state and stop. So whenever you represent something in if else structure, that is basically you are representing, they are you are actually representing that as a tree, that can be represented as a tree, that cannot be represented as a sequence. Okay, right? So in a non-deterministic problem, the solutions are represented through if else statements. So they can be represented only through trees, they cannot be represented through sequences. And many real world problems are actually contingency based problems, that is they are non-deterministic, because you cannot predict exactly. Exact prediction is almost impossible. Fine. Right, now what we are going to discuss is how to represent uh, this non-deterministic problems solution. So there is a so as we already discussed, these if else non-deterministic solutions, not the solutions for the non-deterministic problem should be represented through if else constructs, and that can be represented through trees. So there is a special type of trees called and or search trees. So using and or search trees, the solution for the non-deterministic, or the search operation for the non-deterministic problems, can be represented. Okay, so using and or search trees, the the search operation for the non-deterministic problem can be represented. So this, why it is called as and or search trees? Because it contains two types of nodes. The one type of node is called as or node, and the other type of node is called as and node. So what is an or node? So if you take a non-deterministic problem, it is not that at every step it will be non-deterministic. Some steps will be non-deterministic, some steps will be deterministic. Okay, but as a whole, we say that problem is non-deterministic, because even if there is at least one step is non-deterministic, then we call the problem as non-deterministic. But that doesn't mean that at every step it is non-deterministic. No, in between some of the steps may be deterministic. Right? So deterministic means what? Deterministic means exactly you know that if I apply this action, only this is the result. If you know that exactly at state X, if you apply an action A, only you will get Y. You will not get any other states. If there is no ambiguity, that is called as deterministic, right? So the point I'm trying to emphasize is, in a non-deterministic problem itself, there can be some time that there can be few states which are deterministic. There can be few states which are deterministic, and there can be few states which are non-deterministic. So whichever the state which are deterministic, that can be represented through a node called or node. Okay, the deterministic states can be represented through a node, and that node is called as or node. Right? For example, in the vacuum world, at an or node, the agent chooses any one of the action. There is no ambiguity. It will choose either left or right or suck. It is not that the agent can choose multiple actions. No, there is only one option. Okay, so it's not so this is an example. In the vacuum world problem, at a particular state, let us assume that there is no other option left out for the agent. It can choose only left. It can choose only this action left. And if it chooses left, only this will be the next state. If you know that exactly, then that node can be represented as a OR node, right? And what is an uh, AND node? In a non-deterministic environment, branching is introduced by the environment's choice of outcome for each action. So when you apply an action in a non-deterministic environment, when you apply an action, if the output is not, if the output can be anything, say as we already discussed, current state is A. From the current state, if I apply the suck action, there is no, what do you call, there is no, I cannot confirm what will be the next state. Next state can be either B or C, but action is same. Action is yes only. But still, you cannot say that when you apply yes on the current state, the action will be only B, or I mean the resultant state will be only B, or you cannot say the resultant state will be only C. No, it can be either B or C, right? So in such cases, we represent using AND gate, AND node. Okay. So here we are saying that in a deterministic environment, only branching is introduced by the agent's own choice or node in each state. Then we call it as OR node. Why we say deterministic environment? Actually, we are talking about non-deterministic environment. Then here, why are we saying deterministic? You may ask this question. The reason is, as we already said, even though the environment is non-deterministic, that doesn't mean that at every step it should be non-deterministic. Some step may be deterministic. So overall, the environment is non-deterministic, but in between, say there is a deterministic state. Okay, so with respect to that particular state, you can say that it is a deterministic environment, right? So overall, the problem is non-deterministic, but there is a particular state there the problem is deterministic. That is, in that state, if you apply the action, if you apply some action, you can predict exactly what will be the next state, right? That is only branching. Branching means next state. Branching means what are the option. If I apply an action here, what are the different options I have? That is branching. Only branching is introduced by the agent's own choice. So what the agent action, only the agent's action will determine the output or the next state. Nothing else determines. Okay. And also there is no ambiguity in that. If agents perform this action, only this output. There is no ambiguity like it may be either this or that. In that case, we use OR gate. But if there is an ambiguity, from the current state, if the agent performs this action, it may lead either to this state or this state. In that case, you have to use AND gate, right? So that's the whole concept. Fine. So I think it's clear. So see, in our example also, you see, only we are adding this non-determinism only for suck operation. Okay, there is no non-determinism for moving left and moving right. So if you apply on any state, if the agent applies either left or right, basically it comes under what category? It comes under deterministic category, because the agent clearly knows if it applies left, what will be the next state. Similarly, if it applies right, what will be the next state, right? So when you apply left or right, basically you will be using OR node. When you apply suck, you will be using AND node. So that's the whole concept is, right? So here is an example for AND OR search for the vacuum world problem, starting with the initial state 1. So here this number state 1 represents our original numbering. So this is our state 1, where there is dirt in both the squares and the agent is in the left square. Okay. So this is state 1. From the state 1, what are the possible actions? From the state 1, what are the possible actions? See, there are only 3 possible actions. One is left, other one is right, that we know, other one is suck. But when you apply left, it will remain in the same state only. So we are not considering left. So other two possibilities are what? Right and suck. Okay. So if you apply suck in this place, if you apply suck, what will happen? If you apply suck, what will happen? Can you predict the future exactly if you apply suck? No, you cannot predict. If you apply suck, it may lead into either state 5 or state 7. We don't know what state it will lead into. So here we are using one particular node. This node is called as AND node. This node is called as AND node. When you apply suck on this state 1, the result can be either state 5 or state 7. We don't know what is the result. So that is represented through an AND node. Okay. So that it can be either this or this. So this is actually an AND node. But from the current state, when you apply the rule right, when you apply the action right, is there any ambiguity? No ambiguity. When you apply right, the next state will be only this, what you call, only this vacuum agent will move to the next square, and the dirt will remain in both the square. So that is equivalent to which state? In this vacuum world, that is equivalent to second state. That is equivalent to second state. So in this case, there is no ambiguity. When you apply the right rule, when you apply the right action, it will always lead into this. I mean, from this state 1, if you apply right, it will always move to this state, that is state 2. So here this is called as an OR node. See, in OR node, there is only one branch. If there is only one branch, only that action determines the next state, nothing else. But here the action, the action does not determines the, I mean, the action does not conformly determines the next state. The action is non-deterministic, right? Okay. So now let us continue. Now this is, if it leads to, after applying suck from the state 1, if it leads to 7 state, then that is the goal state. Then you can stop the algorithm here. Okay. But if it is 5th state, if it is state 5, then from here again, what are the things you can do? You can go again, you can apply left, but there is no point in going left. So it will remain in the same state. So you can apply right or you can suck. So now if you apply right, what will happen? Again, if you apply right, there is no ambiguity. Only this will move to, this vacuum cleaning agent will move to the right square, right? That is nothing but 6. That is nothing but 6th state. So this is what node, this is OR node, because here there is no ambiguity. It will only, it leads to only one branch. If from the 5th state, if you apply the right action, you will be taken to 6th state. That's it. There is no ambiguity. But from the 5th state, if you apply suck action, what will happen? In the 5th state, the agent is in the left square, and the left square is already clean. From here, if you apply suck action, either you will get the same state, that is you will be remaining in the same state, that is in the 5th state, that is the I mean, the floor, the left floor will be clean and the right floor will be dirty, or that is one case, or the second case is some dirt can be added to the left square. That may also happen. So there are two possibilities. Either you will be remaining in the state 5, or you will be remaining in state 1. So this is actually an AND node. This is actually an AND node. And now you got here either state 5 or state 1. So if you got state 5, already this is state 5. So you can loop, continue the same. So this same operation you have to loop. So we are connecting here there. Okay, the same thing should be repeating, right? If you end up in state 1, then also loop, then also go to the root node and continue. There is no other option we have, right? Okay. So if you take this path, so this is, we have discussed about this. Similarly, if you take this path, here what happens? Here already you have reached this state. Here, I mean, if from state 5, if you apply right operation, then you will end up in an OR node, and you will reach this state, which is state 6. From state 6, what are the operations possible? Right operation meaningless, because you'll remain in the same state. So other two operations are left and suck. If you apply left, only the agent will move to the left square and the dirt will remain in the right square and left square will be clean. So again, that is very clear. There is no ambiguity. Okay. So there is no ambiguity. So, so what will happen? This is, if you apply left, this is the only result you will get. So this is again, it is an OR. This is an OR node. This is an OR node. Okay. If you apply suck, now if you apply suck, what will happen? Suck will sometimes remove the dirt in its own floor. Always it will remove the dirt in its own floor. Sometimes it may remove the floor in the dirt in the adjacent floor also. It will always remove the dirt in its own floor. Sometimes it may remove the dirt in the adjacent floor also. But in our case, the adjacent floor is always already clean. So you need not remove at all. The adjacent floor is always already clean. So now if you apply suck, what happens? We know exactly now, if you apply suck, you know exactly it will reach into a state where the vacuum cleaner will be remaining in the right floor and both the floor will be clean. So again, this is an OR node, it's not AND node. Normally when you apply suck, it will be an AND node. But in this case, this is a special case. This is not an OR AND node, this is an OR node. Because here there is no ambiguity. Because from state 6, if you apply suck, this dirt will be surely removed and the adjacent floor is already clean. So here in this case, this is OR node because there is only one branch. Okay. Now if you come here, that is from the root node, if you apply right, then the agent will come into the right square and the agent will be in the right square and both the squares were dirt. Now what are the operations you have? You have left, suck and right. But if you apply right, the agent will remain in the same state. So this is meaningful. So let us not consider right. So either left or suck. So if the agent applies the action left, then only this agent will move to the left square, nothing else. So that is the only option and that is determined. There is no change in that. So this is what this is OR node. But if you apply suck, then what happened? Two things may happen. One is this dirt alone will be removed or otherwise both the dirts will be removed. So there are two possibilities when you apply suck. The first is both the dirts in the both the squares were removed and the agent remains in the second square, the right square. Second possibility is, so the first possibility is state 8 and the second possibility is the dirt remains in the left square and the right square dirt is removed and the agent is in the right square. This is again fourth state. This state is nowhere, I think. So again from here you have to continue. Again from here you have to continue. So what you have to continue? This is now the agent is in the right square. What are the possible actions? Left, right and suck. Right is meaningless. If you apply right, you will remain in the same state. If you apply left, what will happen? The agent will just move to the left square. So that can be represented using an OR node. And what will be the result? The result will be the agent will be in the left square and the dirt remains in the left square. And the dirt remains in the left square and the right square is clean. Okay. This is the only option available. So this is OR, right? But if you apply suck, then what will happen? There are two things may happen. One is this right floor is already clean. Okay. And agent is in the right floor. Now, if you apply suck, one option is the right floor may remain clean and agent is in the right floor and dirt is in the left floor. Another option is the agent may add dirt to the right floor also because due to this suck operation, because as per our rule, when the suck operation is applied on the clean floor, sometimes it may add dirt, not all time. So there are two possibilities. So this is AND gate. So this is AND node. Okay. So this is what state. This state is there. This state is somewhere. The agent in the left and the left is dirt and the right is clean. Is this state is anywhere? Is this state is anywhere? No, I don't think so. Agent is in the left and the left is clean. So this is what state as per our agent is in the left and the left is dirt. This is state 3. This is state 3. Okay. So this is state 3 and left is dirt, agent is in the right. Left is dirt, agent is in the right and the right is clean. This is this same state. This is state 4. Okay. Both the states are dirt and the agent is in the right state. This is state 2. Okay. So again it should continue, again it should loop basically, right? So this state, this is already we have state 4 somewhere here. So somewhere here, so this will be a loop. This also will be a loop from the root node. Here, see, this is interesting. From here, what you can do, you can apply either left, right, or suck. Left is meaningless. If you apply right, it is deterministic. If you apply right, it is an or. This is an or, and the agent will just move to the dirt will remain in the left, and the agent will move to the right, and the right will be clean. Okay, right is clean. If you apply suck, what will happen? Suck also now it will lead to R only, R node, because it will surely remove the dirt from the left and agent will remain in the left, and the right dirt sometimes it may be removed, but our right is already clean. So this is also a goal state. Okay. So this is how the search happens in a non-deterministic environment using and or search trees. So in this graph, you can see this bolded, darkened links. They represent the goal state. So this is one particular goal, one particular strategy for goal. Here we don't call it a sequence. This is another strategy for reaching the goal. Similarly, there is also a goal this way, which we have discussed, right? So in case of a non-deterministic environment, the point is the goal the solution is not a sequence. Rather, the solution is a strategy, or this strategy is also called as contingency plan. Okay. So a solution for an and or search problem is a subtree. So this solution is a subtree. And there is another interesting fact. In this subtree, if you see, the leaf node will have a solution, has a goal node at every leaf. At every leaf, there will be a goal node. See, this is a leaf, this is a goal. This is not a leaf because it is looping. When this loop is there, it is not a leaf. It is again going back here. This is also not a leaf. This is not a leaf. This is a leaf, but this is also a goal. This is a leaf. This is also a goal. This is not a leaf. This is loops. Here there is another path is there as we have discussed. So this is an important key aspect you should understand. In an and or search tree, every leaf is a goal. Okay. At every leaf node there is a goal node. At every leaf node there is a goal node. Okay. So so in an and or graph, if it specifies only one action, then it is represented through or node. Okay. If a path includes more than one action, if it includes every outcome branch at each of its AND nodes. So AND node include more than one possible uh, outcomes. Okay, AND node includes more than one possible outcomes, whereas OR node includes only one possible outcomes. So from a node, if there is only one possibility, that is represented through OR node. From a node, if there are multiple possibilities, depending on the depending on the environment, then that is represented through AND, right? So that's it about and or search trees, and that's it about search in non-deterministic environment. Fine, let us stop here. Thank you.